Okay, so yeah, I will talk about MPO representations of algebras. So it's a joint project with Pepe, Albert who's a PhD student in Madrid, Norbert, so we know that the two-dimensional topological order is inherently related to fusion categories. For example, you can create string-like models that are based on a fusion category, and the anions themselves are then described by the center of the fusion category. Or as Lorenz told you yesterday, you can also have sometimes two fusion category inputs, but still the center of the fusion category. The topological order is also understood in PEPS. In which case, we understand that the reason why topological order arises is the presence of some MPO symmetries. And in fact, these MPO symmetries are some representation of these fusion categories. So what I will talk about today is that when someone says fusion category, you can safely think of representations of certain algebras. It's actually known what those algebras are. They are called Hopf algebras. And what I will also talk about is how these representations are related to the MPOs describing, defining the symmetries of topological order types. They are actually the same. All right, so let's jump in. So I want to motivate that why you can think of representations of certain algebras instead of a fusion category. Okay, I will be very sloppy. If you want something rigorous, then read this paper on fusion categories. Okay, so why do I like this result? It's because simply I don't know what fusion categories are, whereas I can think about representations of algebras. So I hope it also helps you to visualize these categories. Right, so what we can start with are representations of groups. Okay, so the main thing with group representations is that you can take their tensor product. So I can define a new so given two representations, I can define a new representation that I call the tensor product representation. That is simply the tensor product of the representing matrices. Okay, so in a finite group, we know that every representation can be decomposed into U-reps. So this tensor product representation, you can also decompose the sum of U-reps. So for example, if I take a U-rep A and B, their tensor product decomposes to a direct sum of U-rep C with some, each of them appended with some. So with ease of notation, I can just write that A fusing with B is the same as sum over C and ABC times C. Okay, so there is also a trivial representation, and this trivial representation has naturally the property that when you fuse it with anything, it leaves the given representation. So if you want, you can write A fusing with unit, the same as the unit fusing with A, and it is A variable. You can also define inverse representation. So you take a representation, you plug in -1, and then have to transpose the matrix because taking the inverse is an anti-homomorphism, and then transposing is also anti-homomorphism. Gives back you the correct multiplication rules. So this inverse representation then has the property, it's easy to check, that if you fuse it with the original representation, then the result will contain the trivial representation and it will contain it exactly once. One, A fusing with A bar it has the unit once exactly. Okay, so I hope this motivates that you can think of representations of groups as a fusion category, but it's a very special fusion category. So if you want, think of fusion categories, you cannot just think of group representations. You have to be more general. What is this more general object? It's actually called algebras that are called Vyckoff algebras. Okay, I will try to motivate. I won't tell it's a definition of Vyckoff algebra because I don't know anything of it. I will try to motivate what the important properties of Vyckoff algebra are. So, okay, to learn what's the underlying structure, let's start with the simplest example, the group algebra. So if you want, it's the same as the previous representations of groups, because representation, I mean, when you talk about representations of groups, you actually talk about representations of group algebras. So basically, yeah, we learned before, we can take representations of tensor product of representations of groups. The same thing, tensor product of representations of group algebras. It's just simply a linear extension. So if you define a tensor product representation, it will be linear. You can just look like this, and then what you see here is a tensor product of representation of group elements that you know that it's just a tensor product of the representing matrices. And then you can just rewrite this expression as phi tensor psi acting on this element here, which is on the sum over G and the G times G. So it can be an any algebra element. What's important to describe, define a tensor product representation is this so-called coproduct. So, yeah, in order to define this tensor product representation, what we have used is a map that maps from the algebra to the tensor product of the algebra. This map is called coproduct. Okay, same way you can talk about inverse representation in group algebras as well. Again, it's just a linear extension of the inverse representation in groups, which is just the inverse and then you transpose. And then you can rearrange this equation. And you can realize that inverse representation on any algebra element is the same as taking the representation of another element of the algebra and then transposing the whole thing. Okay, so and this map that maps this element to this element, which is the linear combination of the inverses, is the map that is called antipode. Okay, so actually Vyckoff algebra is such a structure. So it's an algebra together with a coproduct and an antipode, and this yeah, the coproduct and the antipode satisfy some properties that I won't tell you exactly what. If you're interested, you have the indicators. The important part is that the presence of this coproduct allows you to define tensor products of representations, whereas the presence of this antipode will allow you to define inverse representations. So now that we are over that, I will talk about why representations of Vyckoff algebras are actually MPOs. So again, the underlying reason behind the MPO structure of these representations is simply the coproduct. So if you have a Vyckoff algebra, let's just momentarily forget about the antipode. Just concentrate on the algebra structure together with the coproduct. And actually, let's also forget about the fact that we have an algebra. We just have a vector space and a coproduct. This structure is what is called coalgebra. Okay, so now I will have to tell you what's the property of this coproduct is, the defining property. It's a linear map that goes from B to B tensor B, such that it is satisfies this ugly-looking equation that is just associativity. Let me explain what this equation is. Take any element from your coalgebra, you split it into two with the help of this coproduct, and then you split the first half into two. It should be the same as splitting the element into two and then splitting the second half into two. This is actually what will guarantee associativity of the tensor product in the All right, so you might think that this coalgebra structure is very weird, but don't panic, it's actually very well known. And actually, if you take linear functionals with coalgebra, they form an algebra structure. So when I talk about coalgebras, it's essentially just the dual of algebras, so you can think of algebras. How these linear functionals form an algebra? I can just simply define a product of the linear functionals simply by f tensor g. So f and g are linear functionals. So I can define that product acting on an element v as f tensor g x on the product of the element. So this product, you can check that it's associative. It's just simply the consequence of associativity. Okay, it's also true convergently. So if we start from an algebra and we take the linear functionals acting on the algebra, that structure will form a coalgebra structure. Indeed, I can define the coproduct of a linear functional by its action on the tensor product of two algebra elements. Remember that the coproduct maps from a single, from the linear functional space to the tensor product linear functional space. So it acts on two algebra elements. And by definition, it's just the original linear functional acting on the product of the two elements. Again, one can check that the associativity of the product of the algebra is equivalent to associativity of this coproduct that I have just defined. So, my statement is that this coproduct is very closely related to MPS structure. Okay, so why is it? Well, there is a very easy way to understand it. So if you take repeated coproducts of a vector, so for example, you take an element, you split it into two, then the last part you split it into two, and then again the last part you split it into two, and you repeat it. You get something like this, with graphical notation, and I guess if you tilt your head, you can see that this is an MPS. There is actually a better way to write this object as an MPS, which is way more useful for our purpose. For that, let us choose a basis of the coalgebra, and let Fi be the dual basis. So the basis elements of the dual of the vector. Okay, so if you have a basis and a dual basis, then any element can express like this. Okay, it's not magic. But you can do the same thing with the coproduct of the vector. So you take the coproduct of the vector, you apply the previous relation to the first and the second part simultaneously. Then you get that the coproduct of the vector is the same as sum over ij at site tensor xj times, okay, this is a big number here, which is fi tensor fj. These are linear functionals acting on the coproduct of the element v. Okay, so now if you remember the slide, I told you that this v star has an algebra structure, right? And the product in this algebra is defined exactly through this, this expression. So I can rewrite the coproduct of the element as sum over ij, xi times over xj, and fi times fj. So now I can repeat this, and I can take n-1 repeated coproducts of the vector v. And then what I will get is that I can write it as sum over xi1 tensor and so on xin. So these are basis elements of the vector space times the coefficient that has this very special form that you take the linear functionals fi1 and so on fin, you multiply them, and this whole thing acts on the vector v. Okay, so if you look at this formula, maybe you see already that this is an MPS. Indeed, you can write it as an MPS with MPS tensor is just simply the identity. So this xi corresponds to the physical index, and fi, they form an algebra. You can just take an explicit representation of it. So those are matrices. So this fi has two indices actually, like one left and one right. So this upper two, lower two indices correspond to the linear function of fi. So this v is just actually just matrix that. So this v is not. It's just a matrix representation of the algebra element v in this field space. So, all right. So, okay. So what we have learned here is that if you have a coproduct, so you have a coalgebra, you can think of the elements of the coalgebra as MPSs, repeated coproducts of an element as MPS. So interestingly, this relation between coalgebras and MPS also works the other way around. So if someone shows you an MPS, you can think of it as a coalgebra, representation of a coalgebra. How? Okay, so when someone gives you an MPS, they give you an MPS tensor. Okay, assume that these MPS tensors are defined by the matrices AI. Then you can just simply take the algebra generated by these matrices AI. So A. And then you can realize that the MPS tensor defines a map that goes from the dual of this algebra to CD, simply by phi of f is f acting on the matrices AI. F is a linear function that acts on this space, right? All right, so, but it is easy to see now that the MPS then is sort of a representation of this coalgebra. So if you take an MPS with an open boundary condition, so you're allowed to put any matrix when you close the boundary, then what you get is exactly the phi tensor acting on repeated coproducts of this algebra element, algebra element. Right. So, okay, what we have learned so far is that MPS structure and coalgebra structure are very much related to each other. So, how to apply this for our algebras? Again, in algebra, we have algebra, and the antipode. Let's just again forget about the antipode. Just think about the algebra and the structure. So here is one more property of the coproduct that I haven't told you yet. Is that it's in the V-Hopf algebra, the coproduct is multiplicative. When you take the coproduct of two elements, it's the same as taking the coproduct of the elements individually and then taking their product. Okay, so it's important to note that it will be a bit confusing at sometimes that okay, so A is both an algebra and a coalgebra. Right? And when you take the linear functionals over A, they are also an algebra because of the coalgebra structure of this thing. And they are also a coalgebra because of the algebra structure of the algebra. The A star has a similar structure, so it's both an algebra and a coalgebra. But A star is very different. Okay. These are different algebras. Okay, so just as before, the coalgebra structure of A yields you an MPS representation. Okay, so now I write MPOs simply because yeah, I have an algebra, so I think of these guys here as matrices. So I will do matrices everywhere. But this MPOs representation is nothing, just the MPS structure that comes from the. Okay, so what's important to note here is that these two verticals, so the physical indices, correspond to the algebra structure of the algebra, whereas the horizontal indices, the virtual indices, correspond to the algebra structure of the dual of this structure. Okay, so finally, we arrive to this compatibility of the product and the coproduct. You can check that if you use repeated coproduct, well, then you can also just separate to the product of the repeated coproduct of the two elements. And what happens is that this results in the fact that when you take these two MPO, so two MPO representations of two algebra elements, you take that product, it will be just the MPO that represents the product of these two algebra elements. All right, so basically when you have a V-Hopf algebra, you can think of its representations as MPO algebra. So with the representations you can think of as matrix product operators that you can multiply together, and these matrix product operators will form a closed algebra. Okay, so let me just make a few. The dual algebra. So if this algebra is semi-simple, it means that into a direct sum of blocks. And this MPO structure also decomposes to a direct sum. So the MPO tensor itself decomposes to a direct sum of blocks, and the MPO then you can decompose to a sum of smaller MPOs. So you can always decompose the MPO representation of a V-Hopf algebra that is sufficiently nice to a sum of smaller bond-dimensional MPOs. And these MPOs will correspond, so each MPO corresponds to an irreducible representation of the dual of your algebra. Okay, so yeah, it's known that when you the closeness condition, so when you take, if it happens that you take the products of two such MPOs, and you always get same MPO back. It only happens. It happens if and only if such a relation holds between the product of these two MPO tensors. So if you see the product of two MPO tensors, You can compose it as a single MPO tensor and like linear operator and another linear operator. Okay, so these rank 3 tensors here then are known that so when you check the associativity of like you check the product of these 3 tensors, then it's very well known that the presence of these rank 3 tensors yields to the F symbols. So if you are missing F symbols from the fusion category, this is where it comes from. Okay, so finally, I will talk about that these MPOs that we just created, so the representations of Hopf algebras, are the same as the MPO algebras that pop up in the definition of topological PEPS. So there is this very nice paper by Nick Newton about means and matrix product operator algebras, where they describe actually this part they describe very well. All right, so okay, so what's the so as I told you, and you probably know, the topological order in PEPS is due to the presence of some symmetries, pulling through conditions that you have some MPOs in your PEPS that you can pull through the whole system. So you can, like, using these pulling through equations, you can just take this MPO and pull through the whole system. And then if you, for example, if you define your system on a torus, then you can just insert 2 of these symmetries, and then you cannot detect these symmetries locally. And this yields you the fourfold, Z2 symmetry. It yields you the fourfold degeneracy of the ground state of the toric code. So basically, this pulling through equation is the origin of topological order. Okay, so I told you that I want to turn fusion categories to Hopf algebra. So I also want to talk about topologically ordered PEPS, but instead of using fusion categories, I want to talk about Hopf algebras. It shouldn't be too hard because fusion categories are the same as Hopf algebras, but representations of Hopf algebras. Okay, so it turns out it's a bit tricky. Okay, let's see what are the main ingredients that you have to use to understand the PEPS, topologically ordered PEPS with Hopf algebras. Okay, so as before, let's start from the case where for the G-injective PEPS case. Okay, it's something that is very well known. Okay, a G-injective PEPS tensor looks like after inverting the invertible part of the PEPS tensor is just sum over G tensor G minus 1 over G minus 1. Okay, so what I want to do is to generalize this PEPS construction for Hopf algebras from group algebras. So what I actually need is first I have this sum over G structure. It's actually nothing but the projector to the trivial representation. Okay, so I have this element. It's a very special element of my group algebra. That is a projector to the trivial representation. Okay, what I also need, I need an MPO representation of this thing. Okay. In Hopf algebras, I will have that. I also need 2 types of tensor, as you see here. I have the normal, and I will need an inverse tensor. Right? Like here, G minus 1, I have to act with the inverse. Finally, very important property, the one that gives rise to this pulling through property, is that this element lambda and the antipode are, well, the inverse, are related. take G tensor G, and you multiply H with the first element. It's the same as putting H minus 1 in the second part. Okay. Hopf algebra notation. What happens here is you take this special element lambda, you take its coproduct, you multiply this with H tensor 1, and it should be the same as multiplying delta lambda with one tensor, the antiproducting one, H. Okay, so this is the origin of the equation. Okay, so in principle, you could try just go in Hopf algebras, find a projector, a trivial representation. These are called integrals. The integrals have this very nice property. Exactly, you can try to put this on a, like just do this construction. However, quickly notice that there are some subtleties, and there are many problems. For example, this element won't be translation invariant, and then you will have to make a choice where you start this MPO, or in a general Hopf algebra, this antipode doesn't square to the identity. So the square of the antipode is not trivial, and that causes further problems. So one has to think through what to do. So actually what happens is that one can prove that in every pivot, so it doesn't hold for every Hopf algebra, it only holds for pivotal Hopf algebra such that the dual of the Hopf algebra is semi-simple. One can prove that in such an algebra there is a projector that is translation invariant. Okay, so there is lambda here, and this very nice property that the MPO representation of it is translation invariant. And it also satisfies a sort of pulling through equation. So if you have this MPO, you put an MPO around it, it's the same as putting some other tensor on the other side. Okay, so this tensor will be a bit funny because it's not related to the antipode anymore, it's something different. And so basically what happens is that it renormalizes funnily. So whenever you see two y tensors, essentially you will have to insert something in the middle to compensate for the fact that it's not on the antipode. So the actual PEPS tensor will be an MPO using 4 different tensors. The original MPO tensor, there is this inverse tensor, and there is this boundary condition of the MPO that defines this translation invariant projector. This red dot you can put anywhere around this ring. And then there is this green dot here. Okay. That is just simply because this y tensor randomizes finally. Okay, so with this you can actually create your Hopf algebra injective PEPS, and after a certain amount of work you can convince yourself that it's exactly the same as the traditional MPO injective PEPS defined by again people. Okay, so it's interesting to remark that, okay, so first of all, this construction works for general Hopf algebras that are pivotal and semi-simple. Okay, so you need some extra condition for the PEPS not disappearing on a sphere. Namely, you need sphericity. Okay, this is also well known in DQFT. I think you also need sphericity to be able to define your DQFT on a sphere. And if you want to talk about actual topological order, then you better take a C-star Hopf algebra, which is automatically pivotal. And the representations form actually a very special fusion category. It's a unitary fusion category. okay, if you take a C-star VCOP algebra, then this funny thing happens that this green dot will move around this placket here. So it doesn't matter where you put this green dot, either you can put it here, or here, or here, or here, and you'll get the same state. Okay, so if you have still, I guess, the three-line notation, maybe Lawrence was talking about yesterday. So if you have it still in mind, then this red dot is nothing but the quantum dimension of corresponding to this closed loop, and the green dot is the quantum dimension corresponding to this closed loop in the three-line notation. Right, so yeah, so what we arrived to a topologically ordered PEPS that is actually exactly the same as the MPO injective PEPS. Here, okay, note that you have two fusion categories, just as Lawrence had two fusion categories, one corresponding to the category of the representation of the VCOP algebra itself, and the other fusion category corresponding to the category of the representations of the dual of the VCOP. All right, and I think that's it. So basically what I wanted to tell you to convey is that when people talk about fusion categories, you can think of them as representations of certain algebras. I think it's conceptually simpler, at least for me. Then you can think of the representations of VCOP algebras, so these algebras, as matrix product operator algebras. So even if you don't like VCOP algebras, you can just think of matrix product operator algebras. They are all the same. And finally, you can construct a topologically ordered PEPS starting from a VCOP algebra without referring to category theory, even though you do exactly the same thing. Okay, I think it's conceptually simpler, at least. Yeah, I don't know what fusion categories are, so I'm thinking about algebras more. But yeah, finding examples is way harder in this language, so if you actually want to write down something concrete, you better turn to the fusion category language. That's it.
Plenty of time for questions.
I'd like to make a comment and ask a question. First, Lawrence had in his setup two fusion categories and a bimodule category between them. And the bimodule category is also present in the VCOP algebra setting.
Yeah.
Because you have this co-unital subalgebra, it has a representation category, and that's the bimodule category. Yeah, so it's really a one-to-one correspondence. And my question would be, you said that a tensor renormalizes.
Wow.
Can you explain this for me, maybe on the blackboard?
Okay, so yeah, basically what happens is okay, so what I tried to stress is that the okay, so for the pulling through equation, what you need is you need an element lambda. Then you take the coproduct of lambda and you multiply with an algebra element on the left. You can put to the other side. Okay, so what happens in VCOP algebras is that if you take an integral here, you run into all kind of problems. Your integrals will never be translation invariant. So by translation invariant, I mean that lambda is the same as maybe you know the opposite of lambda. So I want an element. So I don't want an integral here. I want another element here that satisfies this, and yet it satisfies an equation that I can put this algebra element to the other side. Now, if I insist on this being translation invariant, this element won't be, this operation is not the same as the antipode, it's something else. Okay. Okay, what? So the white tensor is not constructed using the antipode, but using this operation. And simply okay, when I say renormalizing, what I mean is that you take the coproduct. So you take this T operation, you chain with the coproduct. You have this funny property that is T times a group-like element times T composed with that there. So if you do the same thing with the antipode, you don't get this in the middle. And this is, okay, so this group-like element is the green dot. This actually, this is an element that implements the square of the antipodes.
Is it an element you choose or that you get from the structure?
I choose this element.
So that's the pivot.
Yeah, it's a pivotal element. So I choose one pivotal element, yeah. And actually,
it enters in the construction of your T.
yes, it enters into my construction of this element, and because of that, it enters into the construction of the T. If you want, T is the same as the up to inverses S tensor G delta.
So is the green dot dependent on the red dot, or are they independent?
They are, well, I would say that the red dot depends on the green dot.
Okay.
Because the green dot, you have to choose a pivotal element. You can choose a very nice pivotal element in which, okay, so the thing is that quantum dimensions depend on the pivotal element that you choose. But you have a nice choice of pivotal element in which the quantum dimensions are all positive numbers. You can choose that pivotal element. The red dot are just the quantum dimensions, essentially. So if you want the red, it depends on the green dot.
Any other question?
So in fusion category case, it's more or less clear, although it's hard, how to go up one dimension. Do you know how to do the same with
in the string net case, it's hard to extend the Hamiltonian to like the full Hilbert space, right? It's only defined in this like subspace. Is it easier if you formulate everything in Hopf?
Can you speak up a bit?
Yeah, sorry. In like the fusion category case with string nets, they're only like defined in this constrained subspace. It's quite hard to extend them to like a nice Hamiltonian that resolves all super selection sectors. Is it easier to do that with a Hopf algebra formulation?
Parent Hamiltonian, you mean nice parent Hamiltonian?
Yeah, like writing the string net Hamiltonian with weak Hopf algebras instead. Is it easier to have a Hamiltonian who's like eigenstates that actually match the excitations instead of just telling you if you're in the ground space?
Yeah, I mean, I can write down some Hamiltonian. I don't know if it satisfies you or not. I mean, it's exactly just these vectors, essentially.
Well, maybe I can say it this way. Can you write like a Hamiltonian where the terms like actually commute on the full Hilbert space and you don't have to project everything into some subspace where the string rules are satisfied?
Okay, so there's Kitaev's construction. Okay, so
Yeah.
it's actually been generalized to weak Hopf algebras.
Yeah, so like the quantum double is much nicer because you can just like make this sort of little object on the Macedon star that tells you all excitation types.
So you can just use that parent Hamiltonian if you want.
But in general, the parent Hamiltonian will not be commuting.
The general parent Hamiltonian is not commuting, but you can use Kitaev's construction. So it's also been generalized to.
I don't know what you mean by that.
Okay, so okay. Okay, so the star term are pretty clear. Okay, so there are, okay, you have two different terms, star and placket terms, right? The star terms are pretty clear what they are, because they have this. MPOs themselves are projectors.
So for, I see. So for all these pivotal decomp algebras, we get this star plaquette type structure.
If you want to write down a Hamiltonian, you need a C-star structure.
Yeah.
Otherwise, you can write down some Hamiltonian, but it will be non-Hermitian. Sometimes it sends your state to 0 instead of leaving it in right under. So the star term is just simply multiplying with this. Whereas the plaquette term will be like you have these 4 spins. Okay, so when you're talking about Kitaev models, we don't think of the PEPs as the degrees of freedom live here, but they live on the edges instead. So you think of these guys, it's one spin. So this is actually the plaquette term, not the star term. And then what you do is like essentially you just trace out this thing, and then you have to double each side. Yeah, you take the coproduct, and then you trace the middle. If you think through, it's exactly the dual of the operation. What you do here, what you do is you project to the trivial sector here, and you do the same here. You project to the trivial sector here. You just have this. In this picture, it has this very funny form. You take the coproduct of each spin. Okay, you can do that because you can always compress these guys to live in the algebra itself. So they don't span the whole matrix algebra here. They live, in a subspace that corresponds to your algebra. So you can actually take coproducts, and then you just trace out in the middle. That's the Hamiltonian. So there is a nice paper about this. Around 2000 or so, someone generalized the Kitaev model to decomp algebras. I don't know how to do it. I think it's maybe a good time to stop. If you have more questions, you can ask during the coffee break. And we'll reconvene in half an hour at 10:50.